Everyone, welcome to Chippy. It's been a while since we had an in-person meeting, so good to see a lot of you here. And we have a bunch of venues lined up for the next few months, so we're hoping to have another more in-person meetings. And we're only limited to basically the speakers at this point, so we need you to volunteer to speak. Thank you for speaking for us tonight. We hope to see more of y'all with different events. Like if you're interested in volunteering or helping out with Chippy, whether it be running meetings or being part of the board or any other activity, please reach out. We'd love to have more participation. Let's see. I guess in the meantime, we can get started with today's meetup. And let's see. I'd like to introduce Adrian, who's going to give 2 talks today. So thank you for that. It's going to be some interesting talks. So let's about Kubernetes and Classic. Yeah. So why don't you take it away?
Yeah, my name is Adrian. I currently work with American Family, it's a company out of Madison. I also do a lot of open source, and as part of that, maintainer on the Encode.org. We do Starlet, Unicorn, and HTTPX. Starlet, you may use ThroughFast API, which is a wrapper around it. And today I'm going to be talking about what's going on inside your web framework. This is mostly going to be focused on ASGI, which is the async standard, but it kind of also applies to WSGI and other frameworks as well. The catalyst for this talk is some discussions we've been having around writing middleware, and we decided we want to promote a lot more to our user base how to write ASGI middleware, and this talk is hopefully going to teach you a little bit about what's going on, enough that you can definitely write middleware. So first, just like a little raise of hands, who here has done async stuff with Python? Okay, that's a lot of you, I'm actually surprised. Who here uses like Starlet or Fast API?
A little bit.
Okay, cool. You don't need to know any of this stuff. I'm just a little bit curious. So the first thing I'm going to go over is kind of what is a web app, or like what I'm going to be calling a web app. Obviously, you can define it in many ways, but I'm going to say, okay, you're getting data over a stream, and you're going to have to make that connection, do some handshakes. That's definitely in the server side of things. You're going to have to parse HTTP from that because you get bytes, and you have to transform that into like headers and body and all that kind of stuff. And that's also going to kind of fall in the server realm. Then you probably have more than one like route or view, depending on what your framework calls it. But like let's say an HTTP path. You probably have more than one of those, and so you have to kind of send each request to each thing that's routing. You might have some middleware that does like authentication and stuff like that. So that's another component. And then finally, there's like your code, your endpoint that you're writing that is, rendering HTML or returning some JSON from your database, whatever it is. So that's kind of how I'm arbitrarily splitting it up into some functions. And I'm going to say that the server is handling the connections and parsing HTTP. And the web framework is what's doing the routing, middleware, and calling your endpoint. And back in like 2003, Spec came for Python via a PEP actually, that said, okay, we're going to like formally define this API in the middle of how the server side talks to the framework side, as opposed to having it be kind of loosey-goosey and have things that they both. And it's called WSGI. It's what Django uses nowadays. It's what Flask uses. It's what most of the sync web frameworks are using. And it's literally just an API, a specification for how something that calls itself a server can communicate with something that calls itself a web framework, so that you can mix and match them and have, like, I don't know, a server that uses threads and a server that uses processes, and use them with the same web framework. Ascii, or ASGI, is the asynchronous version of this. So it's essentially taking the same idea, but modifying it to work with asynchronous Python. So what is the spec? What is the API?
It's actually just one callable for the most part. They take 3 parameters. The first parameter is called scope, and it's similar to the environ parameter in Whiskey. And it's, as you'll see in a sec, it's just a dictionary with metadata. The other 2 parameters are kind of streams. One is a data stream for you to get data from the client, and one is a data stream for you to send data to the client. And I'm calling them receive and send. They have to go in this order. They don't actually have to have names. So it's just the API is a callable that accepts 3 positional parameters with specs that we'll get into in a second. So the first one is scope. Like I said, it's literally just a dictionary. Like if you do type thing that you get, you'll see it's a Python dictionary. It has mostly metadata about the request. One important one that you'll keep seeing in the rest of the slides is a type key. And this is kind of like a discriminated union sort of thing. So there's several different schemas that this dictionary could have. Like obviously, if you have a WebSocket connection, having a method doesn't make sense. But you want to have a method. You want to have like a standard key for the method when it is an HTTP request. So the first thing that you'll do whenever you're writing like a middleware or an app or whatever, say like, okay, what kind of connection is this? Is this an HTTP connection? Is this a WebSocket? And that's what the type key tells you. Then specifically, this is an HTTP connection, so we have a path, a method, and headers. Now you'll notice, like interestingly, the path and the method are pretty straightforward, is what you'd think. Headers is a little bit interesting. You probably would expect it to be like a dictionary itself or like some sort of mapping. It's actually a list of tuples of bytes. And the reason for that is you can have repeated headers, and the spec doesn't say how the server should, if it should merge them at all. It can, but it doesn't have to. And headers also should be ASCII, but they don't have to be. Like the client can send you stuff that isn't ASCII. So basically, the spec is saying, hey, you figure it out. You know, we're not going to define this. The web framework is the one who's going to define what to do if the client says you some weird, you know, Unicode header. So if you do end up accessing the scope directly, as we'll see in a little bit, that's the kind of thing that you need to think about or deal with when you are dealing with ASCII directly. And those are the kind of abstractions that a web framework will give you. It'll parse the headers, it'll make it into a mapping, it'll like join repeated headers, that sort of stuff. But moving on to the second parameter here, receive. Receive is the stream where you're getting data from the client that's calling into you. And it's an async callable, so you can do like await, receive, call, and what you get back is, again, a dictionary, and calling it receive message, some arbitrary type name I made up. But again, you'll see it has a type key, which in this case is HTTP.request, and let's just leave it at that. There's also like HTTP disconnect, like if the client aborted the connection, but it doesn't really matter too much. So you'll see this one is really simple. It just has 3 keys. It's one that tells you what it is, one that tells you here are some bytes for the body, and one that tells you if this is the last message you're going to get for the body, or if you're going to get another one. So we'll see in a sec. It's pretty easy to just like loop through these and like accumulate the body in memory if that's what you want to do. Send is kind of the opposite. You are making the message and you're sending it to the client. So instead of calling it and waiting it and getting a message, you're going to call it and await it, and it's going to send the message. And the schema of the message that you're sending is, again, you have a type. This one's a little bit more complex because you will have to deal with different schemas or keys or for type. So the first one is HTTP response start, and that's where you set the status code and the headers primarily. And after that, you can send body bytes with that. So what would like the most basic app look like? So this is something you could write and run with like Unicorn or another ASCII server with no web framework, no nothing. You'll see I'm taking a lot of shortcuts here. So I'm saying like, I only want to handle HTTP, and I'm just asserting it, and I'm just going to like 500 error if that's not the case. Really, if you were writing a web framework, you'd want to like, well, maybe for that you would 500 or something, but for post, you might want to return a 405 response instead of just a 500 error. So I'm taking shortcuts here, but this is a working web app. You can copy these 10 lines of code, run it with Unicorn, you know, like load the home page, and it will like echo back to you some bytes. And you'll see, like I said, what I'm here is I'm just accumulating the body and memory. I'm just looping over receive, and I'm saying, okay, as long as that more body is true, I do another loop, and if it's not, I break and I have all my body. So in this case, you probably only get one message, but you always handle it as though you could get multiple. And after I'm done with that, I just echo back the body. So I send those two send messages that I was talking about. The start one, which is just the status code and headers. And like, again, in this case, I'm doing a shortcut. I put no headers in there, but really want to do at least like content length, maybe like content type if you were a real web server. Otherwise, your client is not going to be happy. But yeah, it's just an example. And then I'm just sending the body, which is just bytes. And that's pretty much it. That's all a web app is required to do. Yeah, question.
Couldn't you, with Python code routines, replace all the awaits with just yield statements and then remove the async and all work?
Are you saying, like, could you not use the event loop and just manage it all with coroutines?
Yeah, just with yield, it's simple, looks simple enough. Especially if receive internally has a yield with the leading OS.
Yeah, I mean, okay, so you can generally like use coroutines directly, and I can demo a way to do that. I don't know why you would want to do that though, because I mean the whole reason we have like async defs and stuff is to make our life easier. Was that the question, or?
I was just curious.
Yeah, I mean, yeah, in theory, anything that's async def and you're awaiting, you can do without, and that's how it was until like Python 3 point something. I never used that, so honestly, I don't think I could write it and make it work. But I know that in theory you could do that if you wanted to.
So you had to do it in Tornado. But yeah, it's basically the Tornado made it very similar. You just had to use yields.
Yeah,
So,
yeah. I never wrote that, so I don't think I could make it work. But
like
I know you
basic
can.
was a decorator, and then like basically every time you away, you just did the yield, and then the decorator would like collect it all and then manage the coroutines. And
Yeah, I mean the spec is really a callable that returns an awaitable. So if what you return can be awaited, then it will work. And yeah, you can implement like a class implements like dunder await or something that is also an valid ASCII app. So because you're probably thinking like, okay, what is the server doing? This is a very basic stub of what a server would do. Again, I'm taking a lot of shortcuts, like I'm just printing the response, and I am just generating a message. I'm not like connecting to an actual client over a socket or anything, but this is basically what a server would do. It would create the scope dictionary. It would have a receive and send awaitable that are actually hooked up to some sort of socket or stream or something, and then it would call into your app and await you. So yeah, like I said, anything that is awaited that you can await is a valid ASCII app. And the final clarification I want to make about apps in general is if you go into most web frameworks, you'll see they're a class. I was using just functions, but yeah, like I said, anything that is awaitable is valid, and that includes a class implementing an async dunder call. And that's what you'll see in most web frameworks. Cool, so now the next thing is middleware. Middleware is just something that wraps your application, and this is the simplest middleware possible. You're just taking a reference to the application, and then when you get called, you just dispatch to that back to that application. Like in this case, I'm not doing any processing. I'm just calling into the application. There's a middleware that does nothing, but it is a middleware. So if you have an app instance, you pass it as the first argument to this class, you get back an object that is also a valid ASCII app, and that's how middleware works. It's kind of like an onion. You just keep wrapping your app. Some frameworks like Starlight and Fast API give you nice little utility functions. And actually what it's doing is it's kind of wrapping all the internal application while still keeping the outermost object the same so that you can still keep calling into it. So it's a little abstraction over this, but it's still the same idea. You just wrap all the way into the middle. So if you're going to write a middleware, one of the most common things is just like logging the response status code. Well, actually, let's start with the request. So like, let's say you want to, emit a log event every time you get a request. Or you want to do, like in this case, auth. So this is an example of, again, auth middleware is taking many shortcuts, but is an ASCII middleware that will reject some requests. The things I want to point out that I think are interesting is you're probably not going to be writing a pure ASCII web app. That just doesn't really make sense. You'd be doing a lot of boilerplate. So you're probably already using a web framework like Fast API or Starlet. And that means you don't actually have to go and parse the bytes from the HTTP headers and stuff. Like Starlet has internally a class that does that. It takes that list of tuples of bytes and does the header parsing and decoding and whatnot. So you can actually reuse a lot of that functionality, which is going to mean that even if you are writing an Ascii middleware, it's probably not that many more lines of code or that much more complex than if you were doing with a like request response interface. So like in this case, I'm parsing the headers and I'm using Starlet's class to do that. And then I'm also saying, well, if the authorization header isn't in there, I'm going to return a 401. And once again, I'm using Starlet's response class to do that. Starlet's response class is actually an Ascii app. Once you instantiate it with status code, you can call it like an Ascii application. So that's what I'm doing here. And I see now there's an interesting bug here. After that await response, I need to either return that, which is none, or just return, because this is going to keep running. So there's a bug in there. But yeah, so remember, if you are writing an Ascii app, you can reuse functionality from the web framework. You could even instantiate an entire request object here if you wanted to interact with it. Although that's maybe not the best idea. There's nothing much more else interesting in here. We're just doing some fake authentication stuff, checking the token and returning a 403. And eventually at the end, we call it back into the application if everything looks good. So it's, what auth would look like. You check some headers, reject some requests, and otherwise you call into the application that you wrapped. So one important thing to keep in mind is state. Your middlewares, and generally, if you can, you want to make things stateless. And so one common pitfall is saying okay, I need to store some state. I'm just going to store it on my middleware instance. And that would be bad because this same instance is being used concurrently by multiple requests, and you just can't store things there, and it just never makes sense to do so. But you do have somewhere you can store state, because scope is just a dictionary, and that is going to get passed all the way down through the middleware stack right into your endpoint. So if you needed to pass some information from your middleware to your endpoint, for example, let's say you're writing a middleware that times the request and response or something. You might want to save the time your application got the request and then pick that up somewhere else. You can store that in the scope dictionary. So the way you do that is you just add a key to it and put your data in there. The only important rule is you need to remember you need to be cooperative with other things. You're probably not the only middleware or the only application. For all you know, Fast API has 8 middlewares inside of it, even if you don't add any. It actually has 4 or 5. So my suggestion is namespace or do something like that, which I'm not doing a very good job of here. I'm just adding a key called task group. But yeah, I would call it if you have a company name and you wrote this internal, just throw some sort of namespace on there to avoid collisions with other things, and so that when you're reading it on the other side, you're oh, okay, I know where this is. You can search for the string and find it, references to it, that sort of stuff. But yeah, in this case, I'm just creating a task group and I'm storing it there, so I could use this, for example, in my endpoint to kick off background tasks or something like that. This would be a very simple background task middleware. Create a task group, put it in there, my endpoint runs, and then this thing runs. And because of the nesting of the context manager, the response here will be returned to the client before the tasks need to finish. They might finish before it does, but the tasks running won't block the response from being sent. Cool. Modifying request bodies. So then now the other two things we have left that you might want to do in the middleware is we intercepted the headers and stuff, but what if you want to modify or log or do something, interact with the request body? And we'll see the response in a second. Well, it's actually pretty simple. All you have to do is you have to wrap that receive callable and replace it, and then send your wrapped version down into the application. So in this case, I'm saying every time the application requests a message, and that would be if in your endpoint you have a request object and you do request.body, that is going to be pulling data from this stream, and it's going to be calling this closure that you just made here. And so I'm getting the original message, I'm passing it through some fictitious unzipper decompress class that I just made up, but you could have something like that. And then I'm decompressing it and returning it back to the application. Now, again, I'm taking shortcuts here. You'd probably want to do something about the content length and I don't know, maybe change the content encoding that the application is seeing. So in reality, this might be a little bit more complicated. Like Starlet has a class like this, and if you go and you look, you'll see indeed, they don't use a 3-line closure. It creates a class that has references, that keeps a reference to the scope and doesn't send it until it's gotten the first byte from the body. Anyways, it gets a little bit more complicated, but this is the basic idea. If all you want to do is like count how many bytes you're getting, this is all you need. Another one is modifying the response, right? So it's pretty much the same thing, just in reverse. Because remember, send is the opposite of receive. You don't call and get a message. You send the message and then you await and push it away. So in this case, the application is calling us with a message. We're saying, okay, if the message is a response body, because remember, there's also the response start message, and we don't want to decompress that. We're decompressing it, or no, we are compressing it. Again, it's just some fictitious class I made up. And then we're sending the compressed message. Here's another bug. I didn't pass my wrap send into the app. Instead of doing app scope receive send, you'd want to do scope receive wrap send. But otherwise, yeah, that's the general idea. Now, one thing that's really interesting about this is one bug or issue that we've experienced a lot in Starlet relates specifically to this case. Starlet lets you write middleware in a request-response fashion, but it becomes really problematic if you try and read the request body in the middleware. It'll actually hang your entire application with no errors or anything. And that's because you just consume the entire stream from the client, and when you call request read again, now it's a different request instance. It didn't save the bytes onto itself, and you're asking for more message from the client, but there aren't. This method avoids it. So this is one of the primary reasons why you want to write an Ascii application. If you are interacting with the request body, especially, but also the response body, I would highly encourage you to write it in an Ascii style, because it is a little bit more complex. It forces you to deal with the streams and the sends and the receives, but because you're dealing with that, you're not going to run into like issues that just make no sense where your application hangs. You're forced to deal with that complexity. And yeah, that's it. I have 2 references. One is to the Ascii Spec itself, which I encourage you to read. It's not that long. It's maybe like 3 pages. It just has more detail on all these keys. I was going through like what are the allowed values and what if it's missing, that sort of stuff, as well as Starlet documentation, which has most of this stuff and some more stuff and quite a bit of detail as to how you would go about writing it. Cool. Questions?
How would you integrate a database into like that interaction, like on the server side, so it doesn't block?
Like if you have, well, I mean, there's asynchronous database drivers like async.pg, which is for Postgres, and that would allow you to talk to your database without blocking. If you have a sync database driver, you can always run sync stuff in a thread and kind of not block, although it isn't perfectly scalable because you can spin up 1,000 tasks. You can't spin up, you can probably spin up 1,000 threads on a modern computer, but you're going to run out at some point. It's limited.
So how long did it take you to discover why your server was hanging when you were reading the requests that
Oh, well,
had already been consumed?
that, I don't think that happened to me in particular, but it's like a long-standing bug report on Starlet where it did take some time to figure out at first, and we've tried many different solutions to try and solve the problem transparently to users, and none of them are great. You essentially have to compromise in some way. You either have to like store bytes in memory that you might not use and might be a pretty large payload, or you might, we've been through like, oh, what if we override dunder new on the request object and always use the same, make it a singleton sort of deal. There's cons to that because you can have, it's perfectly valid for middleware to then come and replace the stream, like that decompressed one. And now, what if you requested the body before you decompressed it, then it went to a decompression middleware, and then you request it again? Do you get the decompressed body, or do you get the original compressed body? So now you deal with the cache invalidation. And at that point, it's just like, okay, all bets are off. Has anyone like written middleware and like Fast API or Starlet and run into issues? Just curious. Well, if you do, I might consider just writing an Ascii middleware. Plus, that way, if you switch web frameworks, it'll still work.
Right. So my understanding is like every function call that you use within that call stack has to be async, right? Pretty much. Unless it's like it has to return an async call or block.
Yeah. So I mean, you can do some interesting stuff like in this case, you don't actually need to be an async function. In certain situations like this one, we could just, instead of being async and awaiting this, we could just return this object, and that's an awaitable Ascii app. So we're good. We just get rid of the wait here, get rid of the async here, get rid of the wait here, get rid of the wait here, and not do any async stuff. Although you are still returning like an async awaitable. And if you had to make a call to something synchronous, like you were saying, like you might have like some pre-existing database stuff that is synchronous, and you just want to real quick call it from your middleware. I don't know that I would call database from middleware, but if you wanted to, you could just put it into a thread pool and run it there. Any IO, the library that Starlet and Fast API and several other things use as kind of an abstraction on top of async IO provide some pretty nice utilities to say, hey, I have a synchronous callable like that does blocking IO. Please run it in a thread pool and make it awaitable for me.
So if you like call something in that thread pool, put something in that thread pool, and then when it's done running, you get the result back and pass it back.
Mm-hmm. Yeah, well, I mean, the nice thing about these APIs is that they make it essentially look like an awaitable object. So to get the result, you just await it, and then you'll block until it's done. If you had something that did blocking IO, like a synchronous database access, and you did that in your Ascii app and didn't do it in a thread pool, you would block the entire event loop, and your application would not break, but basically not be able to do anything else, no concurrent requests or anything until that thing is done.
Do you have any other questions?
Is there any sort of, I'm not sure there is, but performance increase between Ascii WSGI standards, or is it just async is nice? And
Well, I have a couple answers to that. I'd say writing async stuff lets you very easily do things that would be just too cumbersome or expensive to do with threads. It's not faster. A function call to an async function is certainly measurably slower than a function call to a non-async function. But it makes it very cheap to like spin up something running concurrently, as opposed to starting a thread, which is more expensive. And you can do many of those. So you can do things like, say, like I've written stuff where I wanted to run something at most every 0.5 seconds. I think I was like polling my database, and I didn't want to overload it. So I said, if it takes a second to run the query, I don't want to then run this then I can run it immediately. But if it takes 0.001 seconds to run the query, I don't want to just hot loop my database. So I just created a task that slept for 0.5 seconds, and then essentially joined that with my database query. And so I wouldn't go until the next iteration of the loop until that 0.5 second sleep was done. You could do that with 2 threads, but now you're spinning up 2 threads, and that costs something. That with async, that costs very little, and that's like a perfectly valid way to manage your concurrency and timing of stuff. So I'd say it enables other program paradigms more so than it enables concurrency. Although it does, in the case of a web server, because it is a lot cheaper to spin up tasks than it is to spin up threads, does give you the ability to handle more concurrent requests on the same hardware. But I wouldn't say it's faster. That is, I think, although in practice it does work out that way many times, I think that's just the wrong terminology or the wrong way to phrase it. It's technically wrong. It's technically slow.
What makes it slower than, why is threads less?
Well, there's just more overhead when you have an event loop. Like he was saying earlier, it's actually all coroutines, and then there's like trampolining back to the event loop, and there's like scheduling of when things are done.
So isn't it whenever it hits a wait, it goes back up the call stack and it has like basically a callback?
Yeah, there's.
And then the call stack repeats. Yeah.
Yeah, I mean the simplest way, and this is like super simplistic and probably definitely not how it actually works and technically wrong problem anyways. But you can imagine there's this big while loop running that just has a big list full of callbacks, and it just goes over every single one of them and says, "Are you ready? Are you ready? Are you ready? Oh, you're ready. Okay, I'll like give control back to you." And so every time you wait, you're giving control back to this big while loop that's running. And so again, it's not much, but that is overhead. So technically, async stuff is slower. But again, in practice, if you look at like benchmarks, and if you start up an async web server on your laptop, you can probably handle more concurrent requests that way than you can spinning up like threads in a Whiskey app.
So I think the real benefit would be when you're dealing with real life client, there might be some delayed, like a half a second between requests from the client, and you don't want to freeze up your entire 250 core web server.
Yeah.
Waiting for that half second for the client. So you can have 100 of these, and even if the client's in Australia and it takes 2 seconds to go through the trans-Pacific cable, that one is just waiting in the loop while the Python interpreter just churns to the rest.
Yeah. Yep.
Yeah.
Cool. All right, thank you very much. Right before we do that, I'd like to introduce our sponsor and Ascii and Chris. If you want to go on with. Thank you.
Sure. Thanks everyone for coming. Not much to say. We are hiring, so take a look at our website at mastery.net. If you're interested in the data engineering side, that's the team that I'm on. I'm less familiar with the app stuff and this kind of stuff, but yeah.
What do you do with the apps? What does Ascii do?
Oh, Mastery. So we're actually called Mastery Logistics Systems. We build software for freight brokerages to help automate sales between carriers and shippers.
What's the data stack?
What's the data stack? I can speak to the data engineering side, which is like Apache Kafka, Snowflake, Airflow. So a little bit of Python, like Airflow is written in Python. dbt is a tool that's written in Python. The developers write in SQL. Yeah.
Cloud provider?
Azure.
Like Windows and Linux.
More and more towards the Windows with WSL2.
It's actually a pretty nice setup.
Yeah. Cool. Well, yeah, help yourselves some more food. We got another talk. How much time do you need?
10 minutes.
Yeah, take 10 minutes.
Everyone take a break. Yeah.
Sure.
10, 15.
Yeah.
Do you mind if I ask you an online question?
Yeah, sure.
So if somebody has used Fast API a fair amount but never used Starlight, what primitives does Starlight provide?
Great question. One of the other maintainers actually is giving a talk about that. I don't know if he has like slides and stuff, so I can link you to that at some point. I mean, I kind of know the answer, but I'd rather give you like some actual nice slides instead of me just.
I'm assuming it's not giving you the level of abstraction that Fast API is, but it's the same.
So basically, Fast API is a dependency injection system on top of Starlight. That's
so Starlight has routing and stuff like it.
Starlight has routing, yeah.
Okay, so it's a fairly.
Yeah, Starlight has routing. Starlight has parsing of multi-part forms. Starlight has does all the response stuff. It does all like header parsing. It does the upload file stuff. What Fast API provides is the Pydantic integration, including the schema and the Open API stuff, and the dependency injection.
I didn't realize Starlight provided so much of that.
Yeah.
Yeah, like that's pretty cool. It's pretty
Yeah, because I've heard of Fast API described as like Pydantic and Starlight, but I had no idea how much.
Starlight does pretty much all of the web framework stuff.
Yeah, okay, that's pretty cool.
I love Fast API's like auto generation of the Open API schema. That's like really neat.
Yeah, it's very good. My company uses AIO HTTP, the server. That's what our Python server is written in, which I've never ever run into before, and I've been finding it really very frustrating. But I'm working on convincing to switch to Fast API when I can. But it's just really interesting.
Yeah.
Have you ever used it, or anybody?
Yeah.
You have? Yeah. No, AIO HTTP.
Oh,
I know.
I've used it as a client, never. I've used it as a server, and like I wrote some unit tests for something that already had it as a client. They were like, I needed to spin up a server. I was like, oh, I already have the package installed. I used it for that. I never used it like in production or anything like that.
It's very strange. You write test that it has its own event loop, so it doesn't play
Oh, really?
other basic type code, and that has been a total nightmare for testing. For small stuff, I can see it, but I haven't seen anybody else using it in production for something serious.
Yeah, I wonder if someone makes a AIO-HTTP server wrapper into Ascii, because I know like HTTPX, which is a request like library. I don't know if you ever used it. We have as an HTTP client, you can pass a Ascii app instance into it, and then instead of making calls into the internet, it'll just go straight into your application, which is really neat for testing.
Oh, I see. That's essentially the setup they give you. They give you a test client that calls directly to the application.
Yeah.
But that's what's giving it its own bank, right?
Right.
It comes to something separate. I don't know what the implications would be if you did it either way.
So in HTTPX, we have an asynchronous client.
Yeah.
So it doesn't have its own event loop. So if you use that to call into an asynchronous app, then you probably could just run everything in your own event loop.
That's interesting.
And my next talk is actually about taking control of your event loop.
Oh, good. That'll be very helpful for the test that I'm repeatedly rewriting and working on very recently.
I just get it around this. Stay alive. So what do you figure out to do now? I mean, you can fill it yeah, see, that would sure be I would have said I'm leaving. I'm not learning right now. I know as much. I think that's really not like I was experience right now. Spend 2 weeks like thinking about yourself, right? Yeah. Know the next time, right? Yeah. So get out of that particular hole. Just go like right. Yeah, just stay out of here. Those things are so. Yeah, it is. Yeah, my God, I want to work everyone. It's like you live on the desert. Yeah, no, exactly. I want to go put my backpack and not feel like I'm, Oh, so you have both? I have. Oh,
wow.
I guess that is.
Yeah, well, they don't track
I don't know if
So we
it's.
had one in, February, March, and then April.
Yeah,
you can't do like that once. Then they,
Yeah.
yeah, people get, our sync is there. Usually we did it on, we did it on. So you can just set like a project down. It's not perfect. You're screwing around with all you do is
Yeah, it's hard to do. It's not something that's there. Like I said, I
so you
like we're on
So it's not even
yeah, you pick up the recent in your lockbox. There's a Black Express. On the downside. So, why you're actually thinking it's hard. Yeah, I mean, this is why we have. This is why we have. I hear
So this is also
the entire database. Yeah.
I guess, yeah, we could like, but it's just long as the multiple kind of like data.
those are the kind of things. Yeah, like guys who know every system.
So I mean, like, what
Yeah.
Ross.
Yeah, because I mean, there's one, right, like one master.
Yeah.
It's one copy.
You can make copies, but only really down.
It is really hard to like follow
I've definitely seen that carries a halfway mark. Shouldn't be going into places, you're gonna and you can go change it. Prevent, if there's an emergent that takes a dictionary instead. Well, all of the existing users of that 10 arguments aren't going to switch over immediately. So you have 10 arguments. Outside, you get a lot. I feel like so
I see like.
even though things are undocumented, I still find other or 10th time wandering into Untitled. That's a lot. Like you said, you have zero documentation and type signatures. You would be in our head. Just dictate like, hey, run your type checker while you're running my unit. This when you see one of these stuff outside the box. That's probably okay. We saw when they're
Oh, yeah. When you first get involved, you just maintain that. You maintain your specific
yeah, you can either put it in the street or you can put it in
No, what's the what are you doing?
So I'm just in the team of the entire board. The only things I've really like worked on though are sort of like the framework and we have other stuff like we have a Django REST framework is a big one. I'm not a Django user, so I've never worked on that. So yeah, we have like a database, not a database driver, but like a database kind of wrapper that wraps other drivers and gives you like the common interface into database. It's called, I think it's called literally just database Autopilot. But I don't use it, and honestly not that many people use it. But yeah, I mean, so how did you first get involved? Just fixing several things.
So were you using them for projects?
Yeah, I was using it for projects, and I just like submitted several PRs, like some bug fixes, some features, and they were like, yeah, I'm just like add it as a want more people to be part of the team. No, I mean honestly, like, I go disappear and like no one's gonna allow to not go hard me. Like, hey, we going to do stuff, but it's like a tag. You know, like once a week in a PR sequence, like, hey, you wrote this, like, what do you think of this change? I mean, yeah, there's like no attached. A lot of times people be like, hey, folks, like, I'm, you know, going to be not doing anything. So, I'm traveling around. Be like, okay, cool. Like, we won't pay you on purpose.
Yeah. What's the governance structure? Where they're like, well, I don't even know, like core maintainers.
Yeah, so I mean, there's basically like one guy who created most of the stuff. It's called Ascii. And he's like the owner in terms of like he's the one who has the keys and stuff like he's on board.
It's like a BDFL situation.
No, well, I'd say he tries not to be a BDFL. Like, you know, he set up all the projects, so as long as like two maintainers approve of the RFP mark, so he doesn't have to approve the stuff. But someone has to be, there has to be like a personal account that owns things, and it is his. But he very much like, yeah, his opinion holds weight for a deal, but we have overridden his opinion before.
Oh, really?
Oh, okay. Like he's not like a big technical person, and a lot of the rest of us are, and so like, that type looks too complicated to me, and we'll be like, yeah, it's the easiest way to type it, and we want to type it, so.
Yeah, interesting. Yeah, I've seen that, it's like a common bias, so like, Python.
Yeah.
Yeah. Which one did you start with, like, on the screen together?
So the first thing we did in org is Django REST framework.
Oh, really?
Which is, like, in terms of stars, I think, probably one of the biggest ones. I mean, like, Starlight has maybe like 9,000 stars or something.
But I feel like a lot of people don't want to.
Well, yeah, that's the interesting thing about that. Like, Fast API is like 50,000 stars, and all those people are using Starlight. If you do like type of the request object in Fast API, it's like request. Some things are wrapped, some things are not. If you leave the request is not wrapped, if you leave responses are not wrapped, it's a thing. You go to Fast API, you see a lot of files, anything like responses, where you just like import JSON response from Starlight and re-export it.
That's cool.
Yeah, no, I mean, we have a lot. Download-wise, we have more downloads than Fast API. But in terms of like stars, we have less. And honestly, like, we're very much okay with that because Fast API to some extent bears the brunt. It bears the brunt of users who don't know what they're doing. If you go into their issues, there's a ton of issues. It's like, I'm getting like a syntax error. Can't Fast API fix this? And they're like, how do they do it Fast API?
Yeah, you're not gonna get that.
We get a trickle of the more technical issues. Stuff like the
Yeah, how often is it like how often do you all tag with
quite often, I'd say like about half the issues you get are Fast API. Some of them it's like we get this, and we're like, yeah, we know about it. Like we have an open listing for it as well. Like we do. But sometimes yeah, legitimate issues get brought up.
Yeah. Yeah, because I can't even. I mean, like it's not like an absolute power user, but I know more about Fast API than most people I know who use it, and I think most people who know Starlight.
Yeah. I mean, you can take like a Fast API out and essentially just if you just have to move the stuff that's happening like from your signature, like you put your model in there and calls it, you just move that inside the function, you just accept a single request object, and then like you're like JSON.load, pass that to your model, and you can basically do that.
Good enough. So, what I assume you're about to know
Web develop, like web and data. Yeah.
Do you get to use some of the stuff that you
Yeah, I mean, we have like few services now that are using Starlet.
That is better than the alternative of like working on stuff outside of work. Use it.
Yeah. No, I mean, luckily, like, yeah, I mean, if we made it, it's a bunch of
Ready to get started on the next one?
Yeah, let's do it.
If you don't mind sharing your screen again.
Well, I did.
And
Add you to the
Stop.
all right, we're gonna get started with the next talk. Here we go.
All right. So first off, the first talk was quite factual. It was an explanation of a spec. This one is a little bit more my opinion, and it gets into more complicated topics like concurrency and deployments and stuff that I'm not an expert. I mean, I don't know. It's more of an opinion piece. Please feel free to ask questions and don't take my opinion as gospel by no means. That, and also I'm going to try and infuriate the tech demo gods by doing not only a live demo, but also bring up an entire Kubernetes cluster for it. So wish me luck. I'm starting it now. It's going to take like 5 minutes. We'll see how it's doing in a few minutes. Yep, sounds good. Create this. All right.
We see it.
Nope, that's on my screen. Okay. Yeah, so this talk is about running Python in the cloud. I think there's several things that make it different running Python in the cloud versus like you have a big server with 96 cores and you're trying to run Python, especially with Ascii apps versus WSGI apps. So this is going to be focused on running Ascii apps, which is what we were just talking about, in the cloud. And I'm going to mainly be referring to Kubernetes, but a lot of the same stuff really applies to like Cloud Run and other similar things, or like even serverless. A lot of the ideas are the same. Basically, it should generally apply to anything where you can scale for free and scale almost unlimited, and that sort of thing. So first, a little bit of background. We already talked about Whiskey. This is the logo for GUnicorn, which is the most well-known Whiskey server. If you've deployed a Python application, there's a good chance you have used GUnicorn. So yeah, GUnicorn is a Whiskey server. It's also a process manager, which we'll get into in a little bit. But yeah, for now, Whiskey server. So what if you have an Ascii app? You can't serve it directly with GUnicorn. There's Ascii servers. Unicorn is the most popular, I think, by downloads. Ascii server. There are others out there. If you want to see how you actually write an Ascii server, I actually recommend you go and you look at the one Port uses. I'm blanking on the name here. Look up Port, the web framework. They have a Ascii server. It's very super clean how it's written. That will help you understand it. But Unicorn is the most popular one. We make it in Starlight. We're the maintainers of it. And so what you do commonly is you use gUnicorn with Unicorn workers, which does this sort of thing where gUnicorn handles the connections and some process stuff, and then hands over the sockets to Unicorn. Unicorn then spins up like an event loop for each process and process stuff. And then now we're also adding into the mix. We're saying we're in the cloud, so we're also adding in like Kubernetes. And so now we have these are some of the Kubernetes primitives. Doesn't matter too much, but we have deployments and replica sets, and more importantly, we have pods. A pod is a container, like a Docker container. Let's just say it's Docker that's running, and traditionally you have multiple of them. So keep that in mind. We're already looking at process managers. We're looking at multiple pods, and so our deployment topology is basically like when we get a request, where does it go to? It goes to Kubernetes, let's say. Then Kubernetes sends it to gUnicorn in one of your pods that's running. Remember, a pod is one container, and you have multiple of them. gUnicorn is then going to send it into Uvicorn. Uvicorn is then going to call into, that's the Fast API logo, your Ascii web application. So we have all these 4 things in our chain. That's the request is going through all of them and back and whatnot. So which one of these are required? So my kind of thesis for this talk is that, yeah, you need Kubernetes. If Kubernetes or Cloud Run, again, similar, you're something that abstracts infrastructure unless you say like, yeah, run my container, please. You're going to need definitely your application that you wrote, and I guess the web framework that comes with that, unless you're writing a pure Ascii application, which you all know how to do now. Then you're also going to need definitely going to need the Ascii server, because like we saw, your application doesn't like talk to sockets. It expects a dictionary with some information, and you need the Ascii application to do that conversion and parse the HTTP and stuff. And then we have Unicorn. So do we need that? Most of the time, and with this deployment topology, all it's really doing is being a process manager. And my thesis here is Kubernetes is already a process manager. You don't need Unicorn. That's my thesis. We'll get into why. So here are some of the issues that I've run into and that I think you might run into too with this deployment topology. Unicorn is a process manager, right? So imagine you're running imagine you don't have Kubernetes and you were back a couple of years ago, or maybe people still now, and you have this big 96 core server and you want to run your application. And obviously you don't want your application to just like crash and go down. So one of the very good features that Unicorn provides is it'll launch 96 processes, one for each core of your CPU. If one of them crashes, it'll just kill that process and restart another one. Great. Now your application didn't go down, and you had 96 of them running, so probably you lost a couple of requests, but for the most part, it's fine. Great feature. What happens is Kubernetes is also a process manager. It also has like health checks to see if pods are healthy. And if in each pod you're running 8 processes that are accepting requests, and one of them dies, your health check is probably still thumbs up because the other workers picked it up and are saying, yep, we're good, we're healthy. Meanwhile, Unicorn is like killing your worker. It kills that worker that died and makes a new one. Okay if it happens a little bit, but what if like you have unbounded memory growth? Now Unicorn's gonna like kill your dead worker process that got an out of memory signal from the kernel and start a new one, but meanwhile their health checks are good. And then when you go into your logs, there's all these errors all over the place, and your service is really slow because it's just constantly restarting itself, and you're running out of database connections because you just have things leaving open connections all around, and you're like, well, why didn't my health check fail? And it's because you still had other workers that were healthy and were responding to the health check. And this is kind of the same issue, and this is one of the issues with deployment topology. It's kind of like when you have 2 queues, you have 2 process managers, and that's one too many. So another issue that you can run into is load balancing. So I'm gonna use very rough terms here, and again, I'm not an expert, but I'm gonna say Unicorn uses a polling model. It basically has all these worker processes, and they wake up and they ask the kernel, hey, do you have data for me, or should I wake up and handle stuff? And if not, they go back to sleep. Kubernetes, on the other hand, it gets a request, and it basically round robins around your pods and just sends it to each one. As I'll mention later, there are more advanced ways to do that, but that's the default. So they're kind of two different models. So the thing is, polling works great at a small scale, but it kind of breaks down at a large scale. When you have, your 96 core thing, and everyone's waking up to poll, you can run into an issue. It's called a thundering herd, where basically you're spending more CPU cycles waking up and shutting down and polling than you are actually doing work. Round robin, on the other hand, is terrible for a small scale. If you have just like 3 pods or like 3 processes running, you can definitely end up in a degraded situation where you have first request is easy to process, second request is easy to process, third request is really difficult, and then fourth request is easy to process, fifth request is easy to process, and sixth request is really difficult. So you just keep hitting the same worker with all the difficult requests, and everyone else is just showing. That's terrible at a small scale. But what about when you have like 100 replicas? Well, that's not a problem anymore, because now it's a lot less likely that you would end up just hammering the same process with all the difficult requests. It's going to be, as you increase your replica size, it distributes itself evenly. So my thought on that is, okay, optimize for the hard thing, optimize for scale. Choose the one that's better at scale. Why? Because if you're dealing with small scale, it doesn't really matter that round robin is bad, because you can just throw some more pods at it and it's going to cost you not too much. I prefer to optimize for running at a larger scale. Another thing is scale to 0. With a traditional Unicorn deployment topology, if you want to have 8 workers, you need 8 CPUs online all the time to be able to handle that. And then you also probably want some replicas for redundancy. So, if I've seen a typical deployment topology is like 8 Unicorn workers, and I want like 4 replicas. So at the very least, you're going to be using 8 times 4, whatever the math says that is, CPUs. You're going to be paying for that all the time, even if you're handling 0 requests. Now you're not really going to want to scale to 0, and that isn't the point. But if you do want to be able to scale up and down a lot, it's a lot easier to do when you're using a single CPU per pod or per Cloud Run work or whatever, because then you can say, okay, I want at least 4 running at minimum so that I have some redundancy. I'll scale down to those 4, and then I can scale up. And as you'll see later, scaling is also a lot faster. Kubernetes plays this resource allocation game where really behind the scenes it has 3 96 core computers or something. But you can request smaller amounts of CPU. You can say I want 12 cores or 8 cores to run my Unicorn process. And you can be in a situation where it can't allocate that because you have 4 96 core things, but they're all using 90 cores. So where do you put a process that needs 8 cores? You can't. So it becomes a lot harder to allocate that. And if you're using just 1 core or even less than 1 core, it's a lot easier to allocate things, so you can be more resource efficient. You end up paying for less things to roll, and you can scale up and down a lot faster. That is my thesis on the issues with the deployment topology in general. Now, another thing I want to touch about is from an application development perspective. Having all of these layers makes it hard to do configuration, configure loggers, stuff like that, because now you have to write the Unicorn configuration, but you also have to write the Unicorn configuration, and they both have loggers and who's doing the logging and all this kind of stuff. It gets really hard. One nice thing if you're using just Unicorn is you can run it programmatically, and that means you get to take control of your event loop and you can configure your logging however you want. You can load environment variables or load it from a file. You don't need to make a special file called unicornconf.py and like to put it there. So like this is a unicorn application that'll run. And you'll see here I'm using Pydantic to load some environment variables. I'm just loading the port I want to serve on. And then I have an async def main function which is my entry point to everything. And there I'm loading my configuration and starting my server. But I could also like launch something to run in the background. Or as you'll see in a second, that's a great opportunity to like connect to your database. And then I'm just launching the event loop if you run this as like Python run main.py. One great way to use this is if you, again, use like Starlight or Fast API and other web frameworks, a lot of them have like startup and shutdown events. And the reason those exist is it's basically a contract between the web server and the framework as to like, okay, when I'm starting up, I'll run this, and then when I'm shutting down, I'll run this other thing. Well, it turns out if you can write it yourself, that's basically like a context manager. And in fact, like a lot of database drivers do provide a context manager, which makes it even worse because now you end up having to like split a context manager into two different functions. There are top-level functions, and it gets really clunky. But if you do it this way, like with async PG, you can just use the context manager, and automatically you'll start your server. When your server gets like a sig term signal, it'll stop serving. You'll exit the context manager, close all your database connections, and be on your merry way. No splitting across two functions or stuff like that.
Is async PG a third party or built in?
It is not built into the standard library, no. I don't build it either. I'm not a maintainer of that. But it is a popular async Postgres specific driver. Highly recommend it. It's great. I love it. Cool. Questions so far?
So I'm guessing where you're going with this is you're going to have like a workable pod.
I just don't run Unicorn at all. Where I'm going with this is you can have a main.py file,
Yeah.
and each pod just runs Python main.py when it starts.
Right.
And then that starts the event loop, starts your web server. Before it starts your web server, connects to the database or whatever, passes. This is really nice if you do like dependency injection sort of stuff, which I am doing here with Fast API, because I'm creating my database connection and then passing that in as a dependency to my application. And it makes it really easy to do because it's layered in the right way, as opposed to being like kind of forced to be functions on the top level.
And then does this set up an HBA too, or?
Does this set up what?
Sorry, you're talking about you have like a Kubernetes deployment framework then, right? So you say you're gonna, okay, so I'm gonna deploy. Sorry if I'm moving ahead.
No, please.
So you say, okay, so I'm gonna have like basically an event loop per pod. I'm not gonna have like multiple, like Unicorn running multiple workers with event loops and all. Right. Yeah, and then maybe 3 pods with like whatever, or you're not going to do that. You're just going to be pod and then pod event. Okay. Now, where would you, like if you had to do like a process pool or a thread pool for like as we were talking about earlier, like where would that go? You have a process pool for.
Well, if you mean like a thread pool, like to run the sync stuff, like we're talking about.
Yeah.
Well, I mean, you can run multiple threads with just one CPU, and in fact, like Fast API and Starlight automatically do some threading stuff for you behind the scenes, which has its own set of worms, and I would recommend you avoid. But yeah, you can totally run threads with half a CPU allocated to your pod. Now, it gets a little bit more complicated if you're trying to like do machine learning or something that's CPU blocking. Now you're like, I need to run processes. It gets a little bit more complicated, but for the simplest case, which is a lot of web apps that are just doing I/O, talking to the database, sending some requests to an auth server, doing a little bit of JSON parsing here and there and stuff, this is perfectly fine. Does that answer the question?
Yeah, I think so. I guess I was just kind of wondering, like, if you might end up with more bookkeeping, I guess, because you got to size the pod for the amount, for like
the amount of CPU RAM that you expect that process to use, and versus oversubscribing.
Yeah.
Well, I'd say it's actually easier to set up scaling because
I think I lost the
Just
share.
straight. Okay, let me. I'd say it's easier to set up scaling because it's easier to think about how much CPU a single process can use. The max it can use is 1, right?
Well, except unless you have like a terminal.
Unless you start doing multi-processing inside, and then it gets complicated and you kind of have the same issues. But I wouldn't say it's any better or worse, because if you have 8 unicorn workers and some of them are sometimes, depending on the request, starting up several processes of their own, I think you could use more than 8 CPUs anyways, in which case you're in the same issues.
Yeah, I think they recommend 2 times the number of CPUs in box plus 1.
Right.
And like they're really simple quick start guide.
Yeah, for unicorn. But I mean, I guess my point is, I don't think you're in any deeper water if you start like launching process pools within your web app than you would be if you did the same thing into unicorn.
Well, it's really operating on a single CPU then, right?
Yeah.
So if you launch other workers, it's going to take away from the event loop.
Well, I mean, you can launch multiple processes and not use an entire CPU, like,
Oh, right.
unless each of one of your processes is doing like intense CPU work, then you.
I guess I'm not even thinking more like less about the CPU than about the memory, because I find that when we're trying to pack things into like a Kubernetes node, we usually run out of memory for the request first, right? And you usually want to like, overestimate a little bit per worker.
Yeah.
The memory request, especially because otherwise you get evicted if you get it wrong.
Right.
So.
Well, I mean, you can. Yeah. I mean, it's kind of the same. You just estimate.
With bigger chunks, though. You know what I mean?
Oh, you're saying you have more flexibility?
Yeah.
Yeah, I guess maybe you are allocating memory more efficiently, I think, but I don't know, I've never really had issues with that.
Idea. I get this. I was actually more just, I guess maybe getting ahead of myself in the presentation.
Yeah. I guess, we can think about that. Okay, cool. So I ran some benchmarks. I set up, and this is a cluster I just spun up, which we'll see if it worked. I set up a Autopilot cluster. I have 4 unicorn replicas with 8 CPU each, running 8 workers. Or I have 32 replicas of unicorn with 1 CPU each. So it's the same total number of CPU I'm using, and I think I did the memory, just scaled it as well. And then I made another service with like 16 CPUs to just hammer those 2, because I didn't want my laptop to be the bottleneck. So it's a little bit overkill, and that's why I set it up now, because I don't want to pay like $10 an hour for this to run for days. So now comes the fun part. This is a QR link to the slide. So what I'm going to do is I'm going to go check my deployment, see if it's up. I'm going to put the URLs there for it. And meanwhile, you guys can scan this, and once I put the URLs up, you'll be able to think of it.
There's Bitcoin miners.
Yeah, send me all of your bases so they can be mine.
Everybody got a retirement plan, man.
Shoot, which one is that? So it's going to be the unicorn address. I'm going to put it up here. This is like trying to write in a mirror or something. Okay, so that IP with no security, if you go there, let's see, just open a new tab. Yeah, so if you go to docs/docs, you'll see there's 2 endpoints. One of them is called image, which is just downloading an image I put it on cloud storage, and then just proxying it back to you. So basically it's do a lot of I/O, not really much CPU. And this one is just very, very inefficiently calculate prime numbers. So just basically burn a bunch of CPU and not do much I/O. So you can go there, you can hit those 2 endpoints and try them. Meanwhile, I will get the other IP up. Cool. Nope. This one. Were you guys able to pull it up on like your laptops or phones? Okay. So I don't know, if you want to run work against it or something, go for it. Otherwise, I'm going to open my overkill deployment with 16 CPU where I can also do that. So here I just have an input called load. Let's see. Yeah, so try out. Yeah, so I'm going to be making, we can pump this up a little bit. 2048 connections on 16 threads. I have 16 cores for 30 seconds to each of them. And let's see if this works. I thought I said 30 seconds. That seemed less than 30 seconds, right? It is a live demo after all. Yeah, it's definitely less than 30 seconds. I don't know. I may not be parsing the parameter right. You can hit this. I have canned results from last time I ran it. I'm not going to update the results again. So, I mean, they're pretty similar is the point. And if we looked at my canned results from last time I ran it, oh yeah, I did it with 65,000 clients. And it's pretty much the same. Maybe Unicorn's a little bit faster. I'd say it's a toss-up for both the CPU and the I/O. And I think the reason this is an interesting benchmark is because this isn't necessarily a given. In theory, it is less efficient, or like you can run into problems doing the round-robin thing I was talking about versus the polling. But in practice, in my experience, for every deployment I've done where I tested it, it's not been a problem. And I mean, a lot of other languages and web frameworks deploy that way as well. So,
would this specific benchmark though, like play really well with round robin, right? Because you're hitting it with the same request every time. There's no difference.
Yeah, I didn't try and come up with a pathological case where the 20th request is the bad one, and I just round robin. And here's the thing too, Kubernetes doesn't necessarily promise it's round robin. It's kind of pseudo round robin with a little bit of randomness. And that's just the default. You can also do a lot of much more fancy load balancing with Kubernetes that you just couldn't even dream of with Unicorn. You can do like load balancing based on resource usage on each pod, which might be a great way to go if you're doing like CPU intensive stuff like machine learning. You can do like number of open connections. There's like different routing primitives, and you can even get into like, you can actually deploy like Envoy or Nginx or like a whole nother load balancing layer in there if you wanted to. So I think you have a lot more flexibility. Now, of course, you can also do those things and still have Gunicorn, but then it gets a little bit tricky because you can have even more pathological cases where you have a pod where one worker is overloaded, and the requests keep going to that one or something like that. That is another interesting point. It's like measuring the health of something running Gunicorn. Like if you're doing Prometheus metrics, the way that works is an HTTP endpoint, right? That returns metrics about your server. But now what if that's always hitting the one worker is always getting the same Prometheus request? So you're actually scraping metrics for one process, but your other processes are super unhealthy. Whereas if you're doing the one, Unicorn process per pod, Prometheus and all these tools have ways to deal with running multiple pods. So it's able to aggregate those correctly. Whereas it doesn't have any way of dealing with, there's one pod that actually is multiple workers, and they might each have different health or resource states. Yeah, so these are my benchmarks. I don't know, poke around if you want, load, test it, see if I'm actually saying the truth. So my conclusions from this, personally, I always just deploy with bare Unicorn now. I really like the pattern of taking control of my own event loop. I think it makes it a lot easier to initialize and tear down resources and set up like a composition route for my application if you're into the whole dependency injection thing. I think for most IO-bound apps, it's a perfectly fine pattern. From my benchmarks, it's honestly even fine if you're doing CPU stuff. Now, again, if you're doing like launching processes inside your web app and stuff, then it gets a lot more wonky. But I figure at that point, you probably want to be running your own benchmarks anyways.
Yeah.
So yeah, one of my recommendations is please run your own benchmarks. Every case is a little bit different, especially if you're doing interesting stuff like that. CPU and Python is always a little bit hard. So another case that is definitely you should run unicorns if you have a really large machine learning model or something. One cool thing you can do when you're doing process forking, which Unicorn will do on Linux by default. So basically, it's what's happening if you're running in the cloud. It copies memory on write. So if you load your big machine learning model, then fork the process, and you only ever read from it, you can in theory save memory by not having multiple copies of that in memory. I don't know, memory's pretty cheap though, so that's probably a problem if you're at a big scale and you have a big model. I've never had that problem. We run scikit-learn models, thankfully. But yeah, I mean, there's some cases that this architecture doesn't make sense. I think you should always run your benchmarks, but I think for a lot of people, it can really simplify your deployment topology, simplify your configuration, simplify your app initialization, and still give you the same or better scaling and stuff.
So what I'm trying to understand is G-Unicorn. It basically runs one pipeline. So let's say you get 8 cores of G-Unicorn. It runs G-Unicorn on one of those processes, and then it basically p-opens other processes on other processes, basically.
Mm-hmm.
And then that G-Unicorn basically is kind of like a scheduler and process manager.
Yeah.
Okay.
Yeah.
Yeah, that makes sense what you're doing.
What's it? I mean, I only use Whiskey.
Yeah.
Which is similar to G-Unicorn, right?
Yeah, it is similar. UWSCI is interesting. I've never used it in production. I've bumped around it a little bit. It's a lot more configurable and extendable than G-Unicorn. So I'm very hesitant to say anything about it because I haven't used it. I'm sure you can configure it in a way which makes sense for any deployment. But then you have to deal with figuring out how UWSCI works and configuring it and all that stuff.
It's written in C, so I think it's pretty fast.
Yeah, probably. Yeah. I can do one more little demo here, which is I'm going to make a change to my deployment. And what I want to show here is how quickly the Unicorn deployment rolls over versus how quickly the Unicorn deployment rolls over. And this has to do with what I was talking about scheduling, finding space to put in a process that uses 8 CPUs and all that kind of stuff. So I'm just going to make a pointless change to my application. Oh, no, this is the wrong, here we are. So I'm going to go, where's my mouse? Oh, there we go. Okay, so I'm just going to make some change here and try and, okay, new line sounds pretty safe. I found out the other day there's a way to commit something with no changes, but I do not remember it for life.
Git.
Well, I already committed this, so it's too late.
You changed the route and then.
What?
It's called dash amend.
That's not changing.
Yeah. Yeah.
If you've got a CI server that absolutely will not run the build until it gets a new commit,
Yeah.
that's about the only reason to do that. Even that, it's a really bad fix your CI.
Okay, so I'm just building the images and pushing them.
So using Pulumi, that was the Python-based, or the language agnostic Terraform or what alternative? Is that what that was?
It's not language agnostic. It just lets you write it in multiple languages. So I wrote this in TypeScript. I've tried several of them, and it's my favorite for that purpose. I'm not a TypeScript developer, but it is very nice to do declarative things in.
Yeah.
I would not want to do it in Python.
What is it called? Sorry.
Pulumi. Yeah, it's just an infrastructure as code tool. I find the one thing I find really useful, especially for a demo like this, is it lets you do both infrastructure like the Kubernetes cluster and your containers and builds in the same thing locally. Which in this case, let me run one command and it'll build my container and then it'll push it up to the registry and then it'll cycle my pods with the new image. So it's really nice for a tech demo like this. Arguable if you'd want that architecture in your actual thing. Is it? Oh, okay. So, oh yeah, so it already finished. I don't know if I kind of missed it, but it rolls over all 32 pods in like a second because it's really easy to schedule a single CPU. And as it takes one of the old ones offline, it can now put a new one on. It doesn't have scheduling conflicts. Whereas the Unicorn one, I think it just finished rolling and now it's just waiting for the health checks to go green. But yeah, I mean, the point is, it's a lot easier to scale when you're scaling small things than when you're scaling large things. It's easier to allocate them, so you end up generally paying less, having faster deployments, et cetera, et cetera. That is one advantage of this.
So does one thing I can actually see where Unicorn would have an advantage when it handles multiprocessing is that it has some shared memory functionality between processes.
Yeah, I mentioned that. You're able to save memory if you're using process forking.
There's a Unicorn bus. Okay.
Yeah, I mean, that said, that's not going to be in the cloud though. I think unless you configure it, by default on Linux, it's going to use, or no, it is only really on Linux or Mac OS by default. Like if you run it on Windows, that's not going to apply. I mean, it is an optimization that makes sense in some cases, but I feel like it would be definitely a micro optimization to come right out of the gate and say, I want to save the memory used by the Python interpreter by using Unicorn process forking.
Well, I'm just thinking, like, if you're dealing with large financial data, which is time dependent, time independent, then you split up the job. But
but
you have one process that reads.
Remember, this is only data that you loaded before you started your web server. It's not data that you got in a request. It's not data you read from S3 and are doing number crunching on. It's only like you loaded a big piece of data before you started your web server. And the best example I can think of for that is a big machine learning model. In that case, it makes sense. You load that before you start your web server, and then you save memory because those things can be, tons of gigabytes. Or maybe if you're doing some sort of like route matching thing where you need a big GPS data set. Those are situations where it might make sense. I don't know that I'd want to rely on that though.
You're probably better off using C or Go and go straight to the system calls.
Yeah, at some point, you're micro-optimizing too much. Okay, so now it's taking forever because it's trying to find somewhere to put my 16 pod deployment thing, or my 16 pod benchmark thing. So I'm just gonna kill it. Sad, and tear it down so I don't pay for it.
There you go. Please don't want to remind you.
Thank you. Yeah, I don't want to come back and I left it running for like.
And discovered you just.
Yeah, it wasn't that expensive. I left it running for a day and I got like a $10 bill. And it's not that bad, but I also don't want to just walk away and get a $300 bill at the end of the month. All right, so where are we? And I mean, to be clear, these bills are only because I'm making like I'm using like a total of 48 cores for this. I don't think I have apps that handle hundreds of thousands of requests and they don't need that many cores. This was just to give an example. That's the mail. Yeah, it's on the presentation. So.
So you mentioned like scaling to zero, like auto scaling the. How do you auto scale in your environments, like the pods?
Yeah, so basically what I'll do if I'm doing the run one Unicorn process per pod, I'll just hammer a pod really hard and see how high the CPU gets. And it's not going to be 100% because there's I/O overhead, so it's actually not going to be doing stuff 100% of the time. But it'll get somewhere up there, and then I'll just set the auto scale target very low compared to that. So a lot of times, like on one of my deployments, I have it down to like 0.1. If more than 10% of the CPU is being used, it triggers auto scaling. Because at idle, it's using less than that, and that's the graph I showed. It lets you do like really aggressive quick scaling up as soon as you get a ton of requests, but then also very quickly scale down.
So while the other pods are spinning up, because you don't waste time.
Yeah, there's a lot. You can also like mess with the HPA to like tune how aggressive it is and stuff. I found honestly it's enough to just set a pretty low CPU target so that it starts scaling, and by the time those requests ramp up, it's scaled up I mean, you're not going to scale to infinity immediately. So if someone all of a sudden starts like sending you 1 million requests a second from 0, you're going to have slow requests or something until you scale up. But I think it's about as good as you can get without, I don't know, being Google or something.
And do you find it better to have a fixed memory or memory CPU upper bound on your pod resources, or do you like leave it open-ended so so if one particular request takes a lot of RAM and you like just use it until you fill up the node?
Yeah. Well, the way I deployed on Autopilot, there is no upper bound. I'm not sure exactly what Autopilot does if you just like use up a bunch of RAM. I don't know when it kills you out of memory. There's only requests. There's not limits on Autopilot. On other actual deployments I have, most of it is internal, so we're not really that worried about someone like sending us some malicious payload that uses up all of our RAM or anything like that. We just set like a reasonable limit.
Usually if you have a limit, you just get the element call on the kernel.
Yeah, you'll just get that what I call. Yeah, we just set it to something where it's like we'd rather get an error at some point if we have like a bug that's causing unbounded memory growth. We want to find out about that. Again, we don't want to come back to a huge bill or something, because you can also auto-scale your nodes, and if you have one thing filling up the entire node, then you might auto-scale your nodes. But I mean, we just set something reasonable.
Other questions? All right. Well, thank you very much for that.